Now that we've discussed solving linear systems, let's talk about systems of differential equations. A system of differential equations looks something like this. X prime equal to 5x plus 3y plus t, and y prime equal to 2x minus y plus e to the t. If we want to consider our different variables, our dependent variables would be things like x and y, the things we're taking the derivative of, whereas our independent variable will be the t that comes from this t and e to the t. So when we try to find a solution, we want to know x of t is equal to what? And we also need to know y of t is equal to what? So this is our ultimate goal. Before I discuss solving these, I want to talk about putting them in normal form. And for that, we're going to introduce some vectors. We're going to start with the vector x. This is going to be the vector consisting of x of t, y of t. It's what we're looking for. So this is what it is that we want to know. We're trying to find this vector right here. We're also going to consider the derivative of this. That would be x prime of t, y prime of t. While x and x prime are going to be generic vectors that always look like this, our other two important pieces are going to be unique to the problems. So first we're going to have this matrix A. This is actually called our coefficient matrix because it's the coefficients of the x's and y's. I have a 5x, 3y, 2x, minus 1y. The other important piece is a vector called f of t, and this is the extra piece that we have floating around, the t and the e to the t. It's the extra stuff we're adding at the end that involves only the dependent variable. And so we can actually rewrite this system as this vector x prime equal to a times the vector x plus f. And I'm actually going to prove that this is appropriate, that this is actually the same thing. And this is known as our normal form. So I want to show that this normal form is actually the same as the original set of differential equations. We know that x prime was the derivative vector, x prime, y prime. A was our coefficient matrix, which was 5, 3, 2, minus 1. X was a vector consisting of x and y, the things that we're looking for. And F was the extra stuff at the end, which was a t and an e to the t. If I look at this right-hand side, I can multiply out this matrix and this vector. I would have 5 times x plus 3 times y. The second row would have a 2 times x minus 1 times y. And then I still have the plus t e to the t vector. We also know how to add vectors, so I can go ahead and add these. 5x plus 3y plus t. And 2x minus y plus e to the t. And so if we look, this first row says x prime is equal to 5x plus 3y plus t, which was the first equation in my differential equations. The second one, y prime equal to 2x minus y plus e to the t, which was the second differential equation in my system. Let's look at another one. So this time I have 3 vectors, and I still want to build this in normal form, x prime equal to ax plus f. So I need to figure out what all of these vectors are. Well, x prime is going to be our derivatives, and this time we have 3. We have x prime, y prime, z prime. So this is our vector x prime. This should be equal to our coefficient matrix, so we're going to look at the coefficients of x, y, and z. I have a 2x, 3y, minus z. My second equation gives me 5x minus y plus 2z. And my third equation, negative x plus 2y minus 5z. So there's my coefficient matrix A. Next, we have the vector x, which is our vector of unknowns, the things we're looking for, x, y, z in this case. So that would be our vector x. And then we need to add our vector f at the end, which comes from the extra things we add that only have a t in them. T, e to the t, and t. So this would be our plus f. So we've now written this in normal form. I now want to look at second order linear equations. Something like this, y double prime minus 8y prime plus 6y equal to t squared. So this is a second order linear differential equation. The first thing I want to do is rewrite this as y double prime is equal to 8y prime minus 6y plus t squared. So I'm going to solve for the second derivative. And then I'm going to introduce a new variable. I'm going to let v be equal to y prime. And since v is equal to y prime, if I take the derivative of both sides, v prime needs to be equal to the second derivative. So I can rewrite this. V prime is equal to 8 times y prime, which is v, minus 6y plus t squared. And then I also still know that y prime is equal to v. So I went from a second order differential equation to a system of two first order differential equations. Let's look at putting this in normal form. Here's the system that I just created, and I want to put it in this form: x prime is equal to a times x plus f. X prime are my derivatives. I have the derivative of v and the derivative of y. Should be equal to, a is my coefficients. I have 8v minus 6y, 1v, and then 0y. My x vector is my unknowns, in this case v and y. And then f is what I'm adding at the end. I'm adding a t squared to the v prime and nothing to the y prime. So now I have this in normal form.